So basically what we have learned is the chemical equilibrium will be reached when you have reaction in both directions. The reaction was going forward, making the products, and the products are reacting back or breaking and making the reactants, producing the reactants back. So these are some chemical reactions I have listed. The first one we have already discussed. We were just talking about it, the famous one. So that's a good case of chemical equilibrium where both sides can show decent activity provided they are given the right conditions. And so these are the reactions what we are going to study further. You have SO3 giving SO2 plus O2. You have N2NO2 giving NO gas. And then yeah, this is having a solid as well as a gas. You have, if you would have done a reaction where you pass steam over iron in a tube, you keep iron and you pass, this is your iron, and then you pass steam over it. What happens? This iron gets converted to iron oxide. It becomes Fe2O3 dot FeO, which is your Fe3O4. It becomes Fe3O4 and it releases hydrogen gas. You have H2 gas coming. Now, if you allow it to go away, if the gas goes away, then there is no question of this reacting back and giving that. But then, if this is happening in a chamber, then H2 can react back with this and produce your iron and steam. So, if you have trapped all of this has to be in a certain trapped vessel such that all the reactants, the products and the reactants, they are reaching a certain equilibrium. Now, what kind of reaction would there be such that it doesn't reach an equilibrium? The reactions what we are not going to study are the ones which are heavily one-sided. I would say heavily because nothing is totally one-sided. So I'll list two examples where I have not put the double arrow. You can see I have put a single arrow depicting that it is a one-sided reaction mostly. And why is that so? Why is that so? We all know that a base with an acid, a strong base and strong acid particularly, is going to form a salt and water, and this salt is not going to react back with water to give you the base and the acid. So this is not a reaction what we are going to study under chemical equilibrium. I'll give you a slight idea because this is what we are going to study in great depth later on. uh, NaOH aqueous, what does it mean? It means you have Na plus, you have OH minus. HCl aqueous means you have H plus, you have Cl minus. And when they are put in the same solution, then what do you think? What do you imagine would happen? What is going to happen is this OH minus and H plus is going to cling to each other and become water, which doesn't break back enough to give you H plus and OH minus. It breaks back a bit. There is a equilibrium of uh, 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 a very one-sided one, which is mostly water. It gives you H plus and OH minus, but hardly any compared to what we are going to study, what the concentrations what we are going to study with your NaOH and HCl. So since it has formed water which has joined, so there is no scope of the Na plus and the Cl minus remaining to make your to combine with OH minus and make the and create the base back, or Cl minus to combine with H plus and create the HCl back. There is no chance of that happening. So this is not what we are going to study under equilibrium acid base reactions where you have a salt formed. And then another case would be where you have precipitate coming. You have AgNO3, you have NaCl. Both are soluble things, but when they react gives AgCl, which precipitates out of the solution. So that's the solution, and the precipitate is lying down over there. then the area in what it will be in contact with NaNO3 will be very less, and it won't be able to give back uh, the reactants. So again, this is also heavily one-sided. Again, I would say heavily one-sided, because eventually we are going to study this in detail in the follow-up chapter, like I was talking about this, about the equilibrium of water itself. We are going to study the AgCl solubility also when we are done with ionic equilibrium, and we are doing ionic equilibrium. But as such, these two are no cases of studying a chemical equilibrium, because they are totally one-sided. And if I take the opposite reaction, I would say they don't go ahead at all. So if they're not going ahead, or if a reaction which is going ahead totally towards one side is not a case what we are going to study. We are going to study cases such as these, where both side reaction is possible, and all of these are in an enclosed chamber. All of them are in an enclosed chamber. We are going to study how these reactions can be shifted a bit towards the left or towards the right by varying various factors. So I hope you understand what does the double arrow, what we are indicating till now, what does the double arrow mean. Arrow forward is indicating that the reaction is going forward, and arrow backwards is indicating that the reaction is going backwards. So some places you may see arrows like this made. At times they are making this kind of arrow also to depict an equilibrium. Now let us study one of the equilibriums more closely. Say SO2 gas and O2 gas is in a closed chamber. What is going to happen? SO2 gas, O2 gas, it's at a certain temperature and a certain pressure such that everything is gas. The product which is going to be formed, which is sulfur trioxide, SO3, is also in gaseous form. So at a high temperature it is happening. So initially, when you have only SO2 and only O2, when only SO2 and only O2 is there, it is bound to produce SO3, and the reaction is going to go forward only. So the reactant is SO2 and O2. So SO2 being over here, O2 being over here, they are going to react very fast, because their concentrations were high, their values were high. They are going to react very fast, and they are going to produce this, and this will indicate that there is a forward reaction going. So if I draw a graph of forward reaction, the forward reaction, what do you think? It will be the same rate all the time, irrespective of the situation, or will it go up or go down? What do you think? The forward reaction is going to go down, because the amount of SO2 and O2 is going to reduce. So the forward reaction is going to go down because the amount of SO2 and O2 reduces. It is not because SO3 gives back SO2 and O2. That is not the reason of forward reaction going down. Forward reaction will only depend on the reactants. Only depend on the reactants. So we have a certain rate, say rate forward. Rate forward is going down. So rate forward, I said, depends only on the concentration of the reactants. So square bracket depicts concentration. So concentration of the reactants and a certain function of it. So I'll write F. Mind you, I'm not writing any SO3 over here. Now SO3 is getting formed, and let me put the backward reaction as a yellow arrow. That will be quite low. The rate of that would be quite low. Why? Because the SO3 itself is very less, but then the backward reaction rate is going to grow up it is going to go up and grow. Why? Reverse or backwards reaction is going to increase because SO3 eventually is becoming more and more and more. Why do we say that SO3 is becoming more? Why do we say that SO3 is increasing? After all, it is going to give it give the SO2 and O2 back also. It is increasing initially because SO2 and O2 had a greater rate of reacting, hence a greater rate of reduction, and in the balanced equation ratio, things are going to get formed. So suppose we had I just put some random numbers. Say we had 20 of this, we had 20 of this, and we had none of that initially. Then what is going to happen? What is going to happen? After a while, this is going to react. I mean, after a while, this is going to get formed due to the reaction of these, and they are going to go down in their stoichiometric ratio. It's not like 20 reacts with 20, 2 reacts with 1. So maybe after a while, I can say this is 18, where 2 has reacted with 1, and this is 19. It is 18 and 19. And how much of this is formed? 2 of that is formed. So when we have 18 and 19, still the reaction is pretty much in the forward and only 2 is formed. So the backward reaction has just started, but I can depict with a very heavy arrow forward and a very light or a small arrow backwards. And this is when we say that the rate forward is much faster than the rate backwards, and this is going to increase, this is going to increase, and these values are going to go down, which is depicted in the graph. SO2 value is going down, O2 value is again going down, and what is increasing is SO3 was nothing, but the value is going up. Eventually, as the SO3 value goes up, the backward rate goes up. The backward rate goes up, and when the values of SO2 and O2 goes down, the forward rate goes down, and a time is going to come when both the rates are going to become same. The rate of forward and rate of backwards is going to become same, which is going to happen where this dotted line is depicted. Because when that happens, then neither the reactant nor the product is going to change in its concentration. They are going to remain the same, not because they are not reacting, only because the reacting forward and the reaction backwards are at the same pace. Now if I talk about SO3, initially it was just SO3. So it would start giving SO2 plus O2, and initially the reaction would be all one-sided till a certain amount of SO2 and O2 is made, such that the backward reaction gains some significance. So in that case, I would draw the graph like that, like this. We have only SO3 initially, only SO3, and none of SO2 and O2. Then SO3 starts falling sharply. Why sharply? Because it was a lot, not because these two were not present. I'm again repeating, not because SO2 and O2 was not present. It is only because SO3 was a lot, and this, as soon as these starts forming, they will start when SO3 starts falling down sharply, the formation of SO2 and O2 will go up sharply. Why? Because these are formed because of this. If it goes uh, two down, out of say 20 was a starting, again say it becomes 18, then this will become 2. If it goes 2 units down, this graph, the green graph, is has to be symmetric. It has to go 2 units up. It goes whatever amount down, the other graph will go that much amount up in the at the same given time. And you can see O2. O2 is half of SO2. So if 2 SO2 is formed, 1 O2 is formed. So 1 O2, you can see it is just the half amount what the other is forming. So anyways, as the reaction proceeds, your forward reaction rate, the forward arrow length would reduce and the backward arrow length will increase, and a time will come when the rate forward and the rate backwards are identical, they are the same. And when that happens, then none of the ingredients SO3, SO2, O2 is going to go up or go down in value. It's not that the reaction is not happening, the reaction is happening, but it is at equilibrium, meaning to say how much ever is getting formed is going to react and unform and form the other side.